A group of computer scientists from Germany have discovered a very scary attack called ALPACA. It stands for Application Layer Protocol Confusion. And it is based on the idea that TLS, our beautiful encryption backbone of the whole internet, is built on literally any transport. It's almost detached from the transport layer that is underneath it. So those guys, what they did is like, okay, we're gonna redirect your TLS session to some other server. And while this on the outside doesn't look really scary, it is actually very scary. Specifically, if you have those scary thing that's called wildcard certificate that you can just put on your server, and as long as you have that same top level domain, you're secure. Wink, wink. How about we jump into it and discuss? Welcome to the Backend Engineering Show with your host, Hussein, Nasser, and TLS, guys. I need to talk about TLS a little bit. TLS, which stands for Transport Layer Security, is what encrypts the communication between any two servers these days. Most servers support TLS. Whenever you see this padlock with HTTPS in it, you're using TLS, essentially, between the client, you, the browser, and the server. The server is a TLS server, and it understands how to communicate between these two. And TLS have been built so it is so difficult to break. That is, you cannot just insert yourself in the middle and terminate easily a TLS session and decrypt the traffic. It's very, 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 very difficult. Not impossible. It did happen before. Wink, wink. DigiNotar certificates. You remember all that stuff? Yes. But it is really hard to achieve a fully decryption TLS and man in the middle because of this certificate, of the beauty of certificate and the certificate authorities and this model of authentication, that the server essentially have to present a unique stamped certificate signed by some other third party, which is in turn signed by another third party, which is in turn signed by another third party, which is in turn signed by a root certificate that is trusted everywhere, right? So it's very, very hard to break this thing. Can it happen? Yes, but really very, very hard. So if I give you a certificate, you can easily, quickly authenticate that is actually me. You're talking to Google. Here's a proof that you're actually talking to Google. So if someone intercepted this session, they have to serve you that certificate, right? Which they don't have. They don't have the private, beautiful key of the server that matches a public key that is actually signed in the certificate by another private key belonging to a certificate authority that you don't have. So verification is easy, but breaking this thing is so hard. If anyone out there figure out how to break public key encryption, the whole world basically will collapse. Bitcoin will just drop to zero, literally, right? But nobody did. You cannot break public key encryption, especially when you have a large bit size, right? But so it's very hard to break this thing. But those guys, those Germans, man, the Germans said, no, we will not stand for this. The German says, "Nein, we're gonna fix it." We're not fix it. By fix it, we mean we're gonna break it. The German said, what if I look at the traffic, but instead of actually changing it and pretending to be the server, I'm not gonna pretend to be the server. I'm gonna sit in the middle, right? I'm gonna look at your initiation of this encryption, but I can't reply. I cannot terminate it because I need the certificate to prove that I am the server, which I don't have. But what if I actually just nudge the TLS hello? It says, TLS hello, just go that side. Don't go there. Just go there. Go there instead. You can do that. You can just change the destination IP address. It's not as easy, but you can change where the packet is going. And if you go to another server, you might say, Hussein, If you go to another server, that server has to present that certificate, right? Well, yes and no. If that server receives that TLS hello, the server says, okay, you wanna talk to me? You wanna talk to me? And the server says, okay, here's my rest of server hello, complete the handshake, and by the way, here's my certificate. But what if that server you directed the hello to has actually the same certificate? You might say, you cannot have this. Domains are unique. You cannot have the same domain. But what if it's wildcard certificate? What if your server is actually called bank.com, right? And the other server is called ftp.bank.com. Haha. And you don't want to create a bank.com certificate, and you want to create an ftp.bank.com certificate. So you created a wildcard certificate called star.bank.com that you just slam it to any server really, and it has a single private key, and essentially it works everywhere. So if you can do this redirection successfully as an attacker, you just nudge the TLS hello to go to another server, and that server completes the handshake with you instead. You don't really care to look at the content. You have some sort of control over this. And here's where most of the attacks actually happen. Now we need to go to the actual paper. I'm going to reference it below if you want to read it. There's a beautiful diagram, very confusing to look at if you're just looking at this. What am I looking at? This diagram is very confusing. But we're going to try to translate and kind of, you know, because it's written in German as effectively. I didn't understand anything from the diagram. But if you look, you keep looking and understanding, you can eventually understand. Obviously, that's just me. Some people will look at it, Hussein, you're an idiot. This is clear as a glass. I don't know what that means. Let's jump into this and discuss. All right. For people listening on the podcast, what we're looking at right now is we're looking at two servers. The server is called www.bank.com. It's an HTTPS server, 443. And the other server is ftp.bank.com. Listening on port 990 for some reason. And those two servers share an identical certificate. And this is the wildcard certificate star.bank.com. Because it's very convenient. Slam the certificate everywhere and you don't have to worry. Right? You just have TLS almost for free. You don't have to initiate a certificate for every single server. Very convenient for management. This TLS management. But we're gonna see that this is actually dangerous a little bit. All right, so these are the two servers. The attack starts by directing the user to the attacker website. You have to click on a link. Once you click on that link, and this link is called attacker.com. That's your origin. There is a beautiful HTML page in that attacker's website. And that HTML page does a JavaScript call. It does a post request. So now the origin is attacker.com. That's where we are. Okay, that's the browser thinks actually knows. The browser knows that you are an attacker.com. And the script in attacker.com is making a post request to bank.com. It's just making a normal post request. And this is referred to as a cross-site request, right? Or cross-origin request. Now, let's also assume that the victim here is already authenticated with bank.com. I don't know. This is Bank of America. They logged in to Bank of America. So they have a beautiful cookie with Bank of America. So if you go to bank, you literally type bank.com and you hit enter, the browser will send that cookie to bank.com and it will identify you. It knows that, hello, Mark. Let's say someone sent you a link on Twitter or on the email. And that link points to the attacker website. It's just an HTML website. It looks benign, right? It's very, very simple. It's an HTML page. So you click on that link that goes to attacker.com. Has nothing to do with your bank. You're just going to another website. That website, you do a GET request, you get back an index.html. You get an HTML page. And in that HTML page, the attacker has a script that makes a post request to bank.com. Aha. So far, that's also fine. Okay, the attacker wants to ping my bank. For the longest time, this thing is scary, right? Before same site cookie attribute, this was very scary. And even way before cross origin resource sharing. These things are scary. These to me, they are no longer scary. Yeah, you can make all the requests you want. You are unauthenticated. But for the sake of this scenario, which they barely mention these things, by the way, in the paper. I wish they did, but they have like one column where they mention same site attribute. They should have mentioned this in the beginning. This cannot happen anymore. You cannot do this attack anymore. You cannot just click on an attacker and then all of a sudden the cookie will be sent. No browser sends the cookie anymore except Internet Explorer. And who's using Internet Explorer really? All right. So now you click on the attacker's link. There's a post request that goes to bank.com. Since the browser says, okay, you're going to bank.com, I do have a cookie for bank.com. Should I send it? Most browsers won't, because same site, if the same site cookie is not set, it's gonna set to lax. As a result, lax won't send any cookies, right? Because it's like, hey, this is a third-party cookie. Nope, I'm sorry, we don't say that. Unless the bank explicitly set the same site property to none, the attacker website in this case will actually send the cookie. And now all of a sudden, we made a request which has the secret, right? But before we do all of that, what really happens here? We're about to make a post request to bank.com. But what happened before making a post request to bank.com? We need to do a DNS, right? Okay, what is the IP address of the bank.com? We get back an IP address, and then we establish a TCP connection. The victim establishes a TCP connection with the bank in this case. But here's what really happens. The first request that goes to establish the sense and ACK goes, and the attacker is listening in the middle. Okay, someone is trying to go to bank.com. I know the IP address of bank.com. The attacker is sitting right here. And the attacker will says, no, that's mine. The attacker will complete the TCP connection between the victim and itself, spoofing the IP address of the bank. Hey guys, Hussein from editing. Another way, instead of spoofing the IP address and doing all this mumbo jumbo, the attacker, if the attacker can actually intercept the DNS request for bank.com and present their own IP address, that is more likely of an attack to happen, because this way the client, the victim in this case, they're going to talk to the attacker directly. It's going to establish the TCP connection with the attacker directly, and then the attacker have full control over this. That's actually the script that they shared. They're using man-in-the-middle proxy for this. So that's actually more likely than actually doing a spoofing attack and stuff like that. Back to the video. If you reply back, right, and you establish a connection between this and spoofing the IP address, then the victim thinks it's connected to bank.com, but it's not really. Still, that's not enough. That's not enough for the attacker to actually understand everything. So now the next thing that happens here is, after the TCP connection, is what? Is the TLS handshake. So now the victim here, again, and the victim is executing this on behalf of the attacker because that he visited or she visited the attacker.com website, which has an HTML. Now the HTML has JavaScript running in the victim's machine. That's what's happening here. And now that we do the TLS, a beautiful TLS, where I'm still going to the server. As far as this victim node is still talking to the IP address of the bank. And now the TLS hello goes. The man in the middle looks at TLS and says, okay, I know this is a TLS hello, but I cannot really reply to it, because if the man in the middle tries to reply, what will happen? It will have to present the certificate, which the attacker doesn't have. But look how genius this is. The attacker will just synchronously stop that TLS hello. Says, wait a second. I'm gonna give you a response. Just wait a second. Just wait a second, victim. Just wait. The attacker then just redirect, right? It already have established a TCP connection between itself and ftp.bank.com, and that's fine, right? Because the attacker, let's say, has access to the ftp.bank.com, and it's just a normal IP address. Hey, I'm just connected to you. Let me in, right? So now there is a TCP connection between the attacker and the ftp.bank.com. And now what the attacker does is like just forwards that TLS client hello from the victim, which is destined to bank.com, remember, they forward it to ftp.bank.com. If your FTP, and you might say, Hussein, FTPs, since when FTP support TLS? Well, FTPS does. So if this server supports FTPS, which is built on top of TLS, not to be confused by SFTP, that's a different one. I think FTPS is the TLS one. I always confuse the two. Then the bank will say, oh, someone want to do the TLS hello with me. Sure, I'm gonna respond back with a server hello, and this is gonna work. Why? Because I am gonna give you a wildcard certificate. Start the bank. Now the attacker gets the server hello, which is happening from ftp.bank.com, and the server hello doesn't really have any server name in it. The TLS itself doesn't have anything to do with the name of the server. It's just have the Diffie-Hellman parameters and the certificate, which is also not the actual name of the server. It's a wildcard certificate. So now the attacker just gets that beautiful certificate and then reply back to the victim. It says, hey, here's your server hello. Now it unblocks it and then replies back with the server hello. The victim is clueless. The victim still thinks that it's talking to bank.com, but it's not. It's talking to ftp.com through man in the middle. What is going on here? What is going on? What are you starting to do, Hussein? Well, we're going to continue now. Now we have an encryption channel that is established between the victim by the help of the attacker to ftp.bank.com. Mind you that the man in the middle really cannot see anything here. It's a fully encrypted channel. Yes, they cannot read the text in the channel itself. They cannot see anything. It's all encrypted. It's an end-to-end encrypted between this guy and the ftp.bank.com. So the attacker's like, when he said, this is useless. The attacker still can't read anything, but no, wait. There's something happening. The attacker has control at the victim side here, because remember, you clicked on a shady link. Now I can execute all the JavaScript I want. So the first request, the post request, which is the original thing we wanted to talk about. Now the post request comes. Now I want to send it, and has to, by the way, this whole thing has to be HTTP 1.1. HTTP 2 doesn't work with any of this stuff because you need ALPN, which kind of breaks everything, as I'm going to talk about. This has to be HTTP 1. So there's so many requirements for this to work. So that's why I say very unlikely this attack can happen in the wild. Has to be HTTP 1.1 for this to succeed, in my opinion. Now, the post request happens. Again, you're going to bank.com, right? And let's, for the sake of example, let's say that the cross-site request actually sent that secret delicious cookie of bank.com. Again, the victim thinks it's talking to bank.com, so it's gonna send the cookie of bank.com, which is what the attacker wants. But the attacker cannot just read it because it's encrypted, right? So now the attacker have flow of what's going on here. So here's what the attacker does. The attacker will write a script, and that script is not here. Let's actually go to the script. Where's the upload script? I have all of this stuff gonna be, by the way, they did a good job, right? Giving scripts and all that stuff. This is the script that the attacker executes next to send that post request, right? I want to send a post request to the bank. And what it does, it just sends actual FTP commands through HTTP request. What? Yes. This attack also assumes that the attacker somehow have access to the FTP. How unlikely this whole thing is, to be honest now. I was like, okay, that the attacker has access to my bank, to my FTP bank. What? Well, you might say this is an insider in the bank. They want to carry this attack. They want to... It doesn't make any sense to me, to be honest. It's like this... There's so many variables that is very highly unlikely to happen in the real world for this attack to be successful. But could it be successful? Of course, there is a tiny beanie chance. But we are here to appreciate the tech, to appreciate the German machines. Right? By the way, I'm a big fan of Germany, the soccer team, so I love you guys. We're gonna send user Bob. That's the attacker's name, by the way. Bob. And then password 1234. Type I think this is binary. Passive. Very important. We have to be in passive mode because we don't want to deal with FTP in active mode. No, sir. We don't want to like do two ports. Yikesy. This will never work in active mode, right? Has to be passive. That means a single port downloads and uploads through this channel, okay? And then we're going to store a file name that is called leak. Anything that comes after that store leak, right, will be stored in the file. So this, remember guys, this is the actual body. This is the body of the request. These post request, all this form data goes into the body. And what comes before the body? The headers, right? So all of this HTTP 1.1, the headers, the cookies, the content type, all of that stuff comes before these commands. Never gets executed. So the FTP will start getting these requests that says, okay, content type -- JSON application, text application for www form, whatever. And it says, what the heck is this? The FTP will say, what the heck is this? It's gonna fail. Even the cookie will get delivered to the FTP server, right? Because it decrypts the stuff, right? The FTP will receive that cookie and it says, what the heck is this? It's gonna say invalid command, invalid command, invalid command. Up until we reach the body where we can say user Bob. Oh, I know that stuff. User Bob. Okay. Then password. Then type I. Then this will then put the FTP server in upload mode for that particular session. Now, anything that comes after it will be stored in this file that is called leak, which is literally nothing. Nothing comes after that. That's it. So what I am so confused about, how did we really upload the cookie here? Because the cookie came before the body. The cookie is in the headers. They never mentioned this in the paper. I never seen this. I read the whole paper, didn't see that. Okay, maybe I have missed it. So the only thing that actually this can happen if that request is replied again. You have to refresh the page, right? Or re-execute the script again for the headers to come first again, right? Because now you put the FTP server on that upload mode, and now you have to resend the same request so that we can store the headers and pretty much everything else into that file. That's all right, guys. There's something that I forgot to mention here. This timeout is actually the key for this to work, even if same site property is not set. And this is a little bit of an egg on my face. I discovered this during editing. It's so funny. I read this paper 3 times, and when I actually sat down and record, I started discovering stuff. Here's why this is so dangerous. Now, as I said, when we put the server in FTP mode, right, the headers might or might not have contained the cookie because it was a cross-site script, right? It's a cross-site request. But we successfully put that FTP server in upload mode. And we have a beautiful TCP connection. Look what happens here. After 5 seconds, we are redirecting to target.com, which is the bank.com in this case. We're redirecting the browser from the attacker all the way to the bank itself. Now, technically, I am now going to bank.com as a first origin, as the origin request. So even if the cookies weren't sent in the original cross-site request, they will absolutely be sent in this situation. As long as they are laxed, strict will never work here, because you're navigating. If your cookies are in same site strict, right, and then you have a script that redirects to a bank.com, the browser won't send the cookie if in the strict mode. It will only be sent when you go physically to the bank.com in the browser and you hit enter. That's the only time those cookies will be sent. But most configuration same site cookies are lax, so this will actually redirect you to bank.com, and after 5 seconds you will go to bank.com and you will send the cookie, but the browser will say, wait a second, I'm going to bank.com, but I already established the connection with bank.com, remember, with the cross-site request. So the browser reusability of the connections is the double-edged sword here. If the browser decides to use the same TCP connection that is established, which most of the time, let's be honest, is gonna use it, then you just sent that precious cookie, because now it becomes a first party cookie, is gonna always get sent unless it's strict, obviously. And that is dangerous, baby. Very dangerous. Oh my God. I have no idea how I missed that. So now, this is really dangerous. So, how do we fix this? Chrome and the browser community. Hopefully, to me, the fix is do not share connections. If there is a website, right, if there is a website, attacker.com in this case, making a cross-site request to another website, bank.com, so there is a TCP connection established in the browser, and you redirected to the same, that website redirected to that original, that cross-site website, now we have redirection. The fix here is the browser should not reuse that connection, because that connection is shady. Create a new TCP connection for that puppy to avoid that. I think that would be a nice fix if Chrome, Firefox, people about browser community, if you're listening to this, that would be a nice fix to this, right? Redirection, use the new connection. Otherwise, this becomes very scary attack. All right, back to the video. All right, so that's the upload attack. Option number 1, uploading the cookie secret into the FTP by essentially tricking the TLS session. You've seen what happened though, right? There is so much moving parts, right? The trick to redirect the TLS is very, very scary here. Let's talk about the download attack, which is, to me, that one is really scary. Again, this requires the attacker to have previous access to ftp.bank.com, and they will upload an HTML file or a JavaScript file, okay, that has a script that we need to execute, okay? And let's say this is gonna transfer $1 million from your beautiful account to the attacker's account. Obviously, this is not just gonna happen because there's gotcha and stuff like that. It can't be automated, a transfer like that, but you can steal the cookie here. They have some sort of a script to read the cookie or to send the cookie to somewhere else, and they upload it to the ftp.com. Using the same technique, and instead of uploading, they force the client to actually download that file and execute it. Now, this is very scary because this is a different territory. We're doing the same thing. We're doing a post request. Sure, let's say we're not gonna even send the cookie this time, but we have established this TLS confusion in the backend, right? The attacker in this case is gonna start sending FTP commands to download an existing file. And by doing that, the client, the victim, is gonna download this shady HTML file or shady JavaScript file or shady script into its session. But this is very dangerous. When you actually download that script and that script actually executes in that session as bank.com, the browser will think that you're executing this script within the context of communication between bank.com, and as a result, it's going to execute the script as a first party originator, and that is where it's dangerous. If the browser will think, hey, you're just talking to bank.com, so I'm gonna treat you as if you are literally in bank.com. So it's gonna send the cookies, it's gonna allow you to talk to the bank normally. It's not gonna treat it as a cross-site request, and as a result, bad things can happen. The third attack is the reflection attack, also dangerous in my opinion. And by sending an FTP command that is called open bracket script alert hello world close script, this is the command, right? You send this actual command to the FTP server. The server will says unknown command script script reflect script close hello world. They're gonna reply back to the victim, and the victim, some dumb browsers, will look at the content, and this is called mime sniffing. I talked about it in one of my videos, mime sniffing attack, which is also preventable by adding a server-side header, right? That's called, I think, no sniff, something like that. I forgot what it's called. But here's what sniffing really means. For the longest time, browsers sometimes try to be too clever by half, which means not so clever. And they receive content, right, from a server. The server, usually, the client relies on a property called content type on the server response to tell it what really this thing is. Are you sending me an image? Are you sending me a binary? Are you sending me a PDF? An HTML file? What is this really? But for the longest time, some servers didn't really, let's say, well, we're not smart enough to actually send this reply. And as a result, the application will break. And as a result, because we don't want applications to break, we don't want the Internet Explorer 5.0 to break, we decided to sniff the content and actually determine what the content is and infer the content type from the content by actually sniffing it. All sorts of amazing attacks happens when you sniff, because when you sniff, you try to be smart, but you try when this is an image, it's not really a big deal, but when it's a script, you sniff it and you say, aha, I think it's a script, let me execute it, and it's gonna go ahead and execute that script. You don't want it to execute the script. So as a result, this FTP reflect attack is gonna re-execute this thing and do bad thing. And not only execute it, it's gonna execute it within the context of this session. And as a result, it's gonna execute as a first party request. This is basically the ALPACA attack. I know I've been all over the place, guys, but I suggest you read this paper. It's a good paper. Again, I have some criticism of my own. Just really, if they just did the actual communication, the TCP, how is the TCP connection really happen right here? What is really going on, right? TCP connection wise, I would be very happy. They didn't do that part, unfortunately. Look, if you look at this, you would think, oh, this is just a one-to-one connection here, which is not really, because if the attacker don't actually terminate the TCP connection here, replying, spoofing the IP address, none of this stuff will work, because the victim will have a connection between itself and the bank directly, right? And if you all of a sudden change the destination IP address willy-nilly, first of all, the victim will say, wait a second, I did talk to bank.com IP address. Now all of a sudden I'm receiving IP packets from ftp.bank.com. Reset is gonna do that. So it can never change the source IP address or destination IP address. It cannot do that, because if the attacker did that, the connection will reset. Even if the connection didn't reset, which is impossible, the NAT behind the firewall, right here, is gonna block all the packets. Says, wait a second, whoa, you did a SYN to this IP address, but now the SYN ACK is coming from another IP address. Whoa! You did not talk to this IP address. Block. That's called symmetric NAT. Symmetric NAT, which is most of the machines are behind, allow you to only connect to IP addresses that you actually talked to before. You cannot receive incoming traffic from an IP address that you never talked to, right? That's for security reasons, right? Some firewalls put you in that mode, symmetric NAT. I mean, hey, if you did connect to something, I'll let traffic come through you through that. That's why WebRTC is going through all this nasty stuff with stun and turn servers. Why is it doing all that? Because of the symmetric NATs. You cannot just change the IP address, right? That's why I know, that's my only criticism. They only say, this is what really threw me off. So, for example, if subdomains share a wildcard certificate, an attacker can redirect traffic. What does that mean? What does that mean, redirect traffic? To me, redirect means, oh, just change the destination IP address and we're gonna redirect you to another one. I wish if they made an entire paragraph talking about what is the nature of this direction, everything will be fine. Again, guys, this is all my takes. Obviously, guys, this is just my summary of the paper. Again, it's a great, amazing find, but I really think it's almost very hard to happen. I don't think we need to worry about any of that stuff. Another thing I forgot to mention is this attack can only happen when your TLS has nothing to do with the destination server, doesn't have a clue or hints that tells you which host you're connecting to. Like if you're using SNI, server name indication, which most TLS client does, I think, right? Then the TLS session will have knowledge about the connection transport. It will have knowledge about the destination. And as a result, the destination will block it. And they do mention this in the paper, to be honest. They mentioned the SNI is like, okay, if there's an SNI in the mix, then the destination server, the FTP server, will block the connection. It says, wait a second, this is not really me. But if you don't have it, then it will work. But, and here's what I really loved about the paper. They actually went and went behind SNI and they said, okay, even if you're using SNI, here's where it gets really tricky. If you have the same domain name, but you have your FTP server running on another port, which is, to be honest, that's the most configuration. Most configurations have the same domain. It's just different port, right? The FTP port is like, what, 23? I forgot what it's called. So you have the same host. Bank.com, port 443, that's the web server. And bank.com, port 990. So even SNI in this case won't save you, because the SNI request will come to the server and says, oh, bank.com. Yeah, sure, that's me. Well, it wasn't really you. I was talking to that server, but there is no TLS session, right? There is no TLS extension that tells you, hey, I'm in this server and also this port. Doesn't exist, right? And if you're going to build one like that, you have to break all the libraries. And that's basically an exact quote from that paper. All of this stuff is just all my opinion. I could be wrong, obviously. And again, kudos for the great German computer scientist behind this paper. Amazing work. Thank you so much, guys. I'm going to see you in the next one. You guys stay awesome. Goodbye.